So this is our first live lecture for this week. There'll be another one Friday and Saturday, and this week we're trying, because there's so much stuff in module 3, I'm mainly focusing on the module 3A, so sections 3.3, 3.4, and 3.5. If I have time at the end, I might kind of give a big picture overview of the module B content. Friday, then that session will mostly focus on 5.1 and 5.2, which is over polynomials, with whatever there might be extra time for. And then the Saturday session will focus on 5.3 and 5.4 with the rational functions. So just a heads up that they're not going to be all the same topics this time. You will have recordings available for all of those sessions that you can view throughout the week. And then just a heads up now, and I'll come up with this at the very end also, there will be a link for a form that you can go and fill out so that we know who attended and what section you're in. Your instructors may be offering some kind of incentive or reward for attending these, and the way they'll know that you attended is by you going and filling out that form. But also it's for us to get feedback and find out if there are ways that we can improve this, or different information on how the sessions go. So be prepared at the end to do that. So just a couple things then. If I'll leave this up a little bit so anybody can read this and hopefully figure out if they need to change their audio settings. So I'm not sure what's the proper amount of time to say this. It seems weird. They always like, when I'm attending meetings that have this, they read it out, and I'm always like, it feels weird for them to read out. If you can't hear me, you should do this. I think that's been long enough. Okay. All right, so we'll see that at the end. You can use the chat reactions. So there's different options for how you can participate with questions and so on, using the chat and reactions. Like I said that. So, all right, let's go ahead and get into the content that I have for today. Okay, so we're looking at module 3A for the most part. So we're looking at graph characteristics, transformations, the graphing tools in MATLAB. So starting with just some graph characteristics from section 3.3. So looking at homework question number 5. So section 3.3, you look at basically different ways to describe what a graph is doing. So looking at, is it increasing or decreasing or constant? Looking at where it has minimum and maximum points, and we talk about local versus absolute min max. There's whether the graph is even or odd or neither, and that relates to its symmetry. Symmetry was more explicitly discussed in it's in section 2.3, I believe, which we don't include, but if you want to go back even in the study plan or in the book and look at that section if you need a little bit more about symmetry, but I'll talk about that a little bit as well. So section 5, or this number 5, depending on which version of the question you get, you're going to get this sort of W-shaped graph, but some of them are going to be a symmetrical W versus not. So notice here we have these points that don't quite exactly match with each other on opposite sides. So like we don't have this, that would be if it was symmetrical. So don't pay attention to whether it's actually symmetrical or not. Symmetrical meaning that y-axis is being like a mirror that it's exactly reflected on. But we'll get to that. So in this graph, though, you're asked to look at finding the intercepts, domain, and range.
Lecture class, by the way.
And where it is increasing, decreasing, or constant. and then whether it's even, odd, or neither, which has to do with the symmetry as well. So the intercept, we're just looking at any point that is on either of the axes. So on the x-axis or the y-axis. So we have these 3 points here. When you're asked about intercepts, if it asks you to find the x-intercepts and the y-intercept and has them separately, then all it wants you to do is just list the x values and the y values. So if it asks for x-intercepts, you would just fill in -1 and 2. And then if it asks y-intercepts, you just fill in the number 1, not the order of pairs. But notice here it asks just the intercepts in general. So if I just list -1, 2, and 1, that doesn't tell whether those are x or y values. And notice also it says type an ordered pair. So that'll, if it says type an ordered pair, you need to, if it doesn't say type an ordered pair, then you shouldn't be putting in an ordered pair. And then just make sure your pairs, that it's the x first. So the x for the x-intercepts would be -1, then 0 for the y, 2 and 0 for the y, and then for the y-intercept, 0 for the x, 1 for the y. So make sure you get your x and y straight when you're doing those. All right. Yeah. Just check that. All right, then the domain and range. When you're looking at a graph, you want to think for the domain, you're doing the x values, and you're going from left to right. So I'm gonna have it a little bit. I'm going to turn my video off just so free up a little bandwidth, hopefully for my writing that's happening. All right, so x values from left to right. So I like to think of it as like you have these walls that are going as tight up against that graph as they can go. And then looking at kind of where those line up from left to right. If there are gaps involved, that will affect that somewhat. But so in this case, we're going from -3 up to +3 on the right. And it wants interval notation. The other thing when you're doing domain and range, so if there's an arrow or an open circle, you're going to have parentheses. Otherwise, it's going to be square brackets. So if whether it's a solid dot marked on the graph, or if it's even just a part of the graph that might not actually be marked with a solid dot, but you can tell that the graph goes to that point. So this is one where it'll be square brackets. And then for the range, we're going from the bottom to the top. So I think of like a floor and a ceiling. So range, the domain was the x values, and then the range is the y values from, again, from bottom to top. So we're going from 0 to 3 here. So putting those intervals in, and again, there were no arrows or open circles, so everything using square brackets. The domain -3 to 3. And then for the range, going from 0 to 3. And again, we'll see one later that's a piecewise defined where the range might get a little bit more complicated, but when it's just this single connected line, then it should be fairly straightforward. But notice the range, I'm not just taking, I'm not just looking at the end points of the domain. I'm looking at changing the direction, looking from bottom to top on the graph. All right, so then we have the increasing, decreasing, and constant. So I think the concept on that should be fairly straightforward. The main thing is you want to always be thinking left to right. So think of this graph as sort of you're looking at a horizon line and somebody's walking along it from left to right. Are they going downhill or uphill, or are they on a level surface? But the thing to make sure you get correct is how to give that answer. So hopefully you can look at this graph, as long as you're thinking left to right, that starting here, it's going down. So that piece of the graph is decreasing. And then this next piece here, it is increasing. Then it's decreasing again. And then increasing. Again, thinking left to right. So you're not looking at like, here's a top point and it's decreasing on either side of that. We're thinking left to right. So, but then what we want to give those intervals is just the X value. So we're just looking at what are the X values, what's that X value interval corresponding to each of those pieces. So the Y values are not going into your answer at all. So this first interval is going from -3 to -1. And then we have -1 to 0, that piece, and then 0 to 2. And then the last piece here going from 2 to 3. And then properly, these should be parentheses because we consider those turning points. It's not really increasing or decreasing, it's switching between the two. But MATLAB does allow you to use square brackets, and I would recommend you use square brackets just to keep in your own mind that this is not an ordered pair. It's not an X and a Y value. It's the starting X value and the ending X value. Just be aware if you do have an arrow and you're going on to infinity, then you would need to use parentheses. You'd never put a square bracket with infinity. But so I don't go, when I see this, I don't go and try and find the increase and then find the decrease and then find the constant. I just look left to right on the graph, find the pieces, and then I go and put them in the right spot. So I have the increasing -1 to 0, and then also 2 to 3. So putting those in interval notation. And then just to show it'll accept either for the decreasing if I go -3 to -1. Now what I don't think it'll accept is a mix. So if I use like some, let's see. Yeah, no, it didn't like that. But I think it'll, if I use either fully parentheses, it's fine with that, or fully square brackets. But the parentheses is just if you're looking back, then it looks like an ordered pair. It's not constant anywhere. That would be a horizontal piece, which we don't have. So, all right, then the last thing here, we have the even, odd, or neither. So even is going to be symmetrical with respect to the y-axis. Again, meaning that the y-axis is the mirror. And that means you have to have perfectly matching, if I have a point here at 0, -1, I should have a matching point at 0, +1. And I don't have that quite. It's almost, and depending again on the version of this question, you might get one that has that type of symmetry. So don't assume that yours is going to be just like the one I'm doing. But that's what even would look like on the graph. Odd would have symmetry with respect to the origin. Or you could think of it as rotational symmetry. Where another way to think of it is that a point, if you have a point, you should have a point with the same, with just opposite value X and Y. So if I have -3 positive, like a point -3, 3, if it's symmetric with respect to the origin, if it's an odd function, I should also have 3, -3 down here. So I would have to have this whole thing rotated 180 degrees as also part of the graph, and we don't have that here. So this one doesn't have either of those types of symmetry, so it's not even or odd. Again, if the symmetry doesn't work for you, we have the definitions of even and odd being, well, so I'm going to put this over here just because my pen's acting up a little bit. So even, the rule is f of -x is the same as f of x. And what that means is if I have a point x, y, then the opposite x value is going to have the same y value. So I'm going to have that pair of points with same y value, opposite x value. So for every x, y, there also has to be the opposite x with the same y. If it's odd, then we have f of negative x equals negative f of x. And that's saying for every x, y, I have to also have a point with those opposite x and opposite y. So if you look at the graph and, if you find any point that doesn't have its partner, then you know that it's not whichever of those you're testing for. So, all right. Next topic, just to finish that up. So I want to talk a little bit about average rate of change. All right, so average rate of change. It's the same thing as slope. Now let's see, you don't have anything, value formula sheet. So if you know how to calculate slope, you know how to calculate average rate of change. Slope, you may know y2 minus y1 over x2 minus x1. Average rate of change, you probably are given in the course packet f of b minus f of a over b minus a. B and a are just the x values. And the difference is then you have to use the function to find the y values. So average rate of change, step one, the way I would do it anyway is all right, so step one, find the y values. Step two, calculate slope. So you'll be subtracting the y values from each other and the x values from each other and dividing. All right. I'm not going to do an example of that, but just to give that information. Then again, I'm not going to do example with min and maxes, but I do want to just talk a little bit about min and max. Hopefully, again, the idea of a minimum and a maximum, you know what those words mean. So min, that's right. A minimum would be a low point on the graph of some kind. A maximum would be a high point. Local, thing to note for local, there can be multiple, but endpoints do not count. So to be a local min or max, it has to have graph on both sides of it. So endpoints don't count as local min or max. But then when we have the absolute, we are looking at the highest and the lowest points. These are going to correspond to the endpoints of the range. So wherever the lowest point is, that would be the absolute minimum. Highest point would be the absolute maximum. If there's an arrow or an open circle, then you wouldn't have, like, if that would be the highest point. So if the range has parentheses, then you would have no absolute min or no absolute max corresponding to that. As far as notation, sometimes you'll be given this form. So technically the minimum or the maximum is the y value that occurs at a particular x value. So you fill in the y value of the point, and then you'd fill in the x value inside the parentheses. So just that standard f of x equals y. For the ordered pair, sometimes you'll be asked something like, what is the minimum value? So you answer the y value, and then they ask, what are the x values where that occurs, or something like that. So you'd be filling in the x values and the y values separately from each other. So just watch for that. But hopefully not too complicated with that. So then that brings us to piecewise defined functions. And so I'm going to look at question number 20 on this homework. All right, so piecewise defined function here, we have the f of x, 3x if x is not equal to 0, 2 if x equals 0. All right, so for the domain of this function, of any piecewise defined function, we're going to look at kind of what happens if we combine those if things. So we have if x doesn't equal 0, so here's 0, so that covers everything other than 0. And then we have if x equals 0, so that fills in that gap. So that fills in that gap, and we have everything covered. So in this case, the domain is going to be all real numbers. I assume whoever that was, if you did have a question, you could put it in the chat, but I'm assuming that was an accidental unmuting there. All right. The intercepts for a piecewise defined function get a little bit tricky, especially with the x-intercepts. So the y-intercepts, for any function, the y-intercept is always f of 0. You plug in 0 for x. So when you're evaluating a piecewise defined function, whatever you're plugging in for x, you have to look at what rule it follows. So here we have 0, x is 0. So is that if x doesn't equal 0, or if x equals 0? It's the if x equals 0. So we're using then the f of x equals 2 part. So that's the y-intercept for this function. For the x-intercepts, though, we're looking for what about y? What makes the function result equal 0? So I have to do both of those. 3x equals 0 and 2 equals 0. But 2 never equals 0. 3x equals 0 when x equals 0. But then I have to check if I do get an x value, would that x value go into that piece of the function? So, but here, because if x equals 0, it's not going to get plugged into the 3x. It's going to get plugged in to the 2. So we're not going to get that 0.00. It's doesn't get plugged in there. So that one doesn't actually happen. So the only intercept then, and here again, it's not specified x or y, so we're putting in the ordered pair. We have 0, 2. When we plug in 0 for x, we get 2 for y. And that's all. All right, then you're choosing the correct graph. So for the graph of this function, we have, for the most part, if I look at, I have my x. So here's my x-axis and y-axis. And for everything other than 0, I have this 3x. So y equals 3x. That's a diagonal line. So slope of 3. So it's going, up 3 units for every 1 unit to the right. The y-intercept is 0. But at 0, it has that gap, because the 3x doesn't apply when x equals 0. When x does equal 0, the y value is 2. So we have this going on with the graph. So I'm going to look for the graph that matches that. I don't want the dot over to the side. I want it above. And this graph, part B, or graph B here, that's a slope of 1. It's going up 1/1. So I need this one. So you need to know something that's also from chapter 2 as far as just how to graph straight lines. So if you need to review that, you might need to review that. But then it asks you to use the graph to find the range, and you have these various options. So you have this question of isolated values versus not having isolated values. So let's say I have a graph. Well, first off, let's look at this graph, and then I'll talk about some of the other options. So this graph, the range, if you want to think about taking the whole graph and just flattening out onto the y-axis, what happens? I end up covering everything above 0 and everything below 0. So the range in this case would be everything from -infinity to 0, not including 0, and then everything from 0 to infinity. Okay, let's say I have a graph that looks like this. Maybe I have, maybe instead of a diagonal line, I had a curve that went like this, and then had that gap, and then had the point. So now, if I look at this whole graph, I have this bottom part, and then there's a gap, and there's no graph there. And then we have this point. So this would be an isolated value on the range on that whole, there isn't anything right above or below that, any part of the graph. So it's off by itself. So here we would have something like, we would have the interval from -infinity to, let's say this top is like at 2, wherever that is. And let's say this is 5, then I would have that single point. So it would go into the curly braces, and we would have that set with just that single point. Maybe I have a graph. Sometimes you'll have graphs that do something weird like this sort of stair-steppy thing. So then if I look at where that's hitting the y-axis, is just getting these individual y values. So you'd have these multiple isolated points. So you just have, maybe -2, -1, 0, 1, just this list of individual y values that are showing up and nothing in between them. So you could have multiple isolated values. Or if I just if my graph is just a horizontal line, let's say y = 2, then the only y value that's going to show up on the whole graph is 2. So it would just be that one isolated value and nothing else. So that's pretty much the possibilities that you have. You could also have something where you have more of a gap. Maybe I have a graph doing something like this, and then somewhere else, if it's to be a function, maybe it's doing this, then it's going straight up and not crossing this line, and then maybe it's down here. So maybe there's a gap in between, and so it's rather than having just a hole, it has a bigger gap. So that could also happen. But yeah, so in this case, we just have no isolated values. There aren't any individual points where there's one point on the graph and there isn't any graph surrounding it, even though we had that point on the graph. But as far as the y values, when you smash the whole graph, flatten it onto the y value, onto the y-axis. So we're just going to have this interval from -infinity to 0, and then the union symbol, and then from 0 to infinity. Again, anytime you want to use, you can click on these buttons, or if you hover over them, it'll show it the shortcut that you can type in if you prefer typing things. So it's \cup for the union symbol, \inf for infinity. And so that's piecewise defined functions. Okay, and that brings us to transformations. So in section 3.4, you're looking at some basic functions and what they look like. So to start with, you need to know a square root graph is something like this, starting at the origin. A square graph is this parabola shape starting at the origin. Absolute value is the V shape. Cubed is, it's not sure how to describe that shape, but it's sort of like the square, but the one side is flipped. Those are the main ones you'll see and need to be familiar with. But we want to look at how we can change those graphs where it's still the same basic shape, but we move it around. So think of all the things, if you've ever manipulated a picture, like put a picture into a Word document and you can change its size, you can pick it up and move it around on the page. You can stretch it just vertically or horizontally. You can flip it horizontally or vertically. All of those things where it's still the same basic shape though. So what those are going to do is you're still going to have, if it's a square root, it's going to stay square root. It's not going to change to square or cube or anything else. But the way those types of transformations happen in the graph is adding numbers, subtracting numbers, multiplying by numbers, changing to a negative. So if we put them all together, everything that can happen, you'll have something like this. We're not really doing or worrying about, well, okay, I'll talk about a couple other things separately. So here we would have a negative multiplied by the function would be vertical. Anything outside is vertical. So the negative and the A and the K, those are all vertical. So that would be a vertical flip. So that would be a reflection over the x-axis. So if I'm going to flip it vertically, that's going to go over the x-axis. The A is going to be the vertical stretch or compression. I don't think in MATLAB you really need to know which of those it is, but just to note the stretch is if it's bigger than 1, compression if it's smaller than 1. The stretch is going to make it taller, and then it's also going to then appear narrower. So if you think of, if you've watched like Charlie and the Chocolate Factory, where the kid gets shrunk and then he gets stretched and then he ends up super tall and skinny, that's what the stretching is doing. And then a compression is going to make it shorter, and that's also going to make it wider. So if you think of, again, if you've ever watched like YouTube videos of people like compressing things with like a hydraulic press type thing, and it flattens out, but it also sort of spreads out sideways. Or even just think of taking in a balloon or a ball and pressing it down, it gets shorter, also gets wider. It's not really getting, it's looking wider visually. Then we have when you just add a number, subtract a number, that's going to shift vertically. So up if positive, down if negative. Now, when we go to what's inside the function, by the way, that f is standing in for the actual action, the square root, the square, the cube, etc. So when we say inside the function, that means inside the square root, inside of the parentheses that have the square. So like, that's inside. But if I do something like this, that +2 is outside. It's not included in what's being squared. So it's not about being inside parentheses. It's about being inside, or you can think of happening before the actual main function action that determines the shape. So let me change colors, just I've gotten kind of messy here. So this is going to be the horizontal shift. The reason it shows is I have it as x minus h. So however you want to think of it. But if we add inside, that's going to shift left, and subtracting is going to shift right. So it feels kind of opposite. If you do x minus h, then x plus 2, then h would be a -2. So that would be the actual shift, would be the -2. So that's a way to kind of make it switch. But that's kind of up to you how you think about it to keep track of that. And then the other thing that can happen is, like, if I have f of -x, that would be a horizontal flip. But if you think about what these graphs look like, the only graph that is going to be affected by a horizontal flip is the square root. The cube root would get flipped, but it turns out that with the cube, that a horizontal flip is the exact same thing as a vertical flip. So the only graph where you'll actually do horizontal flips would be the square root. So let's look then at how you do these graphs. One other thing, I did want to look at the formula sheet just to show you none of the stuff from these sections, section 3.3 through 3.5, it's not in the formula sheet. Neither is any of the stuff from 5.1 through 5.4. So all this stuff that you're doing in module 3, you need to learn, memorize, whatever. It's not going to be on any of your references that you're going to have on the test. So make sure you're putting in that time to learn and remember all of these rules. And I know it is a lot, but that's what we're doing here. All right, so I am going to look, starting back a little bit to number 15 to show there's a couple different graphing tools. So this one is just graphing x cubed. And so it starts by having you do these 3 points. And I'm going to assume you can figure out -1 cubed is -1, 0 cubed is 0, and 1 cubed is 1. But then when you get to the graphing tool, so let's look at this graphing tool a little bit. You have a straight line. To determine a straight line, you need 2 points. For a cube, or sorry, for a quadratic, you have to have 3 points. For a cube, notice if you look at this tool, there are 4 points marked on there. It had you identified 3 points, but we actually need 4 to get the graph. So when I click this, I do those 3 points that I had. That's not enough to get my graph. So I need to figure out a correct 4th point. This was just x cubed, so I just need to pick some other number and cube it. So I could do 2 cubed is 8, or 3 cubed is, well, pretty much I'm left with 2 cubed is 8, or -2 cubed is -8 to fit on the graph. But I'm not just randomly picking a point. I'm going to make sure. And if you have trouble seeing the point, you can look up here. It shows that order pair that you're at. So I can do that 4th point to get that graph. If I was needing to do a quadratic, then I would potentially just have 3 points, and that would be enough for the graph. So that's how that graphing tool works. Mostly, though, the graphing tool you're going to be using, I'm going to look at number 37. So this graphing tool, when you click on it, this is used just for cube and for square and cube. So if it's a square, use the what's called a parabola shape. If it's cube, you use the cube shape. So in this example, I have 5 times x plus 1 squared plus 4. So let me just write that to the side here. So this is all right. So we have 5 times x plus 1 squared plus 4. Yeah. Okay. So I look at this. The 5 is a vertical stretch. Any number it's outside of the square that's happening. The plus 1 in here, that's a horizontal. And so I need to think of that's going to be the opposite direction. It's going to be left 1 unit, or I can think of it as a -1 shift horizontally. The plus 4 outside of the square is going to shift up 4. But I don't have to actually figure out what the graph looks like. I'm going to click on this quadratic tool. And if you look up here, it says click the graph to plot your curve. I can click anywhere. It's going to take me to the starting point of just x squared. And then I use this box to put in those actual transformations. So I have the vertical stretch compression. That's just that number that's out front. So I'm just going to type that in. Horizontal stretch compression, you shouldn't be doing anything with. I'm pretty sure on any of this homework, you shouldn't be doing that. Then I have the vertical shift here with the slider. Sometimes you'll be typing in the vertical shift. Sometimes you'll be using a slider. So my vertical shift here was up 4. Just make sure you watch that number that's popping up. It doesn't always line up well with the grid that's marked there. But we have up 4, and then the horizontal shift, in this case, it was left 1, so going to the -1. And you can see it moving on the graph, so you can make sure it's going the right direction. I didn't have any reflections, so I don't need to do that. So there's my graph. But using the same tool, let's see how it would look to graph something else. So I'm going to say, say we have -1/2 times x minus 4 cubed plus 7. So first the cube, that tells me I need that shape graph. The negative is a vertical reflection. So that's a reflection over the x-axis. The 1/2 is going to be the vertical, in this case, compression, but it doesn't specify one or the other. The -4, that's a shift, horizontal shift. And it's going to the right 4, so it's a +4. Again, switching the sign on that, the +7 is a vertical, it's up 7 units. So I would click on the cube tool, click anywhere on the graph, and then put in the vertical stretch of compression being the 1/2. I'd go ahead and put in the reflection. Make sure you put in the reflection before you put in the vertical shift. So let's say if I put in the vertical shift and put it up 7, and then I reflect it, notice it reflected over the x-axis and it changed that vertical shift to a horizontal, or changed the shift up to a shift down. So do the reflection before you do the shift. We have it in the horizontal shift +4. So that's how you'd do that when there's even reflections involved, and all those pieces. So that's that tool. When it comes to square root and absolute value, those will be multiple choice, so you won't be using a graphing tool on those. But just to show then, so moving away from MATLAB, just to look at kind of how this works. So let's say we have f of x equals -2 square root of x plus 1 and then plus 4. So the basic square root of x has the starting point and goes up and to the right. This graph, the negative outside is a vertical reflection. The 2 is going to be a vertical stretch. So vertical reflection, we're flipping to be going downward, and then the stretch is going to make it kind of a steeper graph vertically. The +1 is going to be a shift horizontal, shifting it left 1 unit. So it's going to move left 1 unit. And then the +4 up 4 units. So going up. So it's going to end up, and with the shift, the way I think about that is what does it do to the starting point? So this point here was at 0, 0, is now going to be left 1 unit and up 4 units from that. So there's my starting point, and then I have the general shape of it going somewhat more steeply, but down and to the right. It'll be multiple choice, so then it should be a matter of finding the one that's going in the right direction, has the right starting point, and then maybe kind of recognizing the stretch happening. So for another example, all right, so for another example, let's say I have 1/2 square root of -x -3. The -3 outside. So I have then a vertical compression. The negative inside the square root is going to be a horizontal flip. And then the -3 shifting that down 3 units. So my starting point, instead of being at 0, 0, is going to be 3 units down from that. The vertical compression means it's going to be, if this was the standard square root, it's going to be flatter than that. And then it's flipped horizontally, so it's going to be facing the other way. So something like this. So these might be helpful to kind of sketch them out, get an idea of what they should look like, or at least look at, kind of think about each of those pieces and what they're going to do to the graph, and pick the graph that best matches those changes. Then the next thing I want to look at is sometimes you'll be asked to write an equation from a list of transformations. And there it matters when you have the same direction. So if you have a vertical, say a vertical shift and a vertical reflection, you need to make sure and apply them in the order given. So the kind of key here is that vertical changes need to apply to the entire previous result. So let's look at an example. Let's say I'm starting with x squared, and one problem says to shift down 3 and then reflect over the x-axis, which is a vertical reflection. But then another might, what if we do this in the opposite order? So reflect over the x-axis and then shift down 3. So, all right, applying the shift down 3, that's going to be subtraction outside. So I have the x squared, I'm going to just stick a -3 on the end of it. Then reflect over the x-axis, I'm going to make the whole thing negative. So I need to apply a negative, not just onto the x squared, but onto the whole thing. And so it turns into negative x squared plus 3. Visually, what's happened is I've taken my x squared, I've shifted it down 3 units, and then I've reflected that last result over the x-axis, changing that down 3 to an up 3. On the other hand, if I first do the reflection, I get the negative x squared, then I shift down 3, so I'm just taking that negative x squared and subtracting 3. Now they don't interact. I just get the negative x squared minus 3. So I've done, in this case, first the reflection and then the shift, and they don't mess each other up, so to speak. So just watch out for that. If you have a shift, a vertical shift, followed by a vertical reflection, the reflection is going to switch the direction of the shift. So, okay, that's what I had for these 3 sections. But I guess before I jump into maybe doing a big picture overview of Module 3B stuff, is there any of these topics that you want me to go into more detail on, or do other examples of, or anything from you guys? Any questions? And I guess maybe it can take a while if you actually have a question to type a question. So I guess say yes if you're going to have a question, but so far I'm seeing it looks like not. So
Can you
all
hear
right.
me?
Yeah, go ahead.
Okay, well, this is back like at the beginning of module 2B, 3.1 and 3.2.
Okay.
I was working out one of the problems to where I had to grab, it was question number 34, actually, 3.2.33, I guess was at the top of it. But anyway, on the example, when it said to view the example, the third step of it, you had to make a chart, the X and Y chart. And my question is, like, how did they come up with the numbers under the X? Because they weren't given in the question. So do you just fill them in with like 0, 1, 2, 3, and 4? You just automatically.
Yeah, you should be able to just pick any numbers. So
because there wasn't, those numbers weren't automatically given. So I didn't know if I just like pulled them, you know, out of my mind, or if it was numbers I was supposed to already automatically know.
Yeah, let me just see what's the best way to do this. So I'm just going to go. So as I'm answering this question, if you ever want to go back and look at past homework,
Yeah.
As far as I understand, it won't let you open it within Ivy Learn, right? So you have to go through the Ivy Plus bookshelf
Yeah, you
and
can
go out.
review it.
And then you can view it. But so there is a way to do it. You just have to go out. So it sounds like you know that, but just so I'm in case somebody else who's here or who's watching the recording didn't know that, you go to your student grade book and you can find things you've worked on. So you said this was module 2B, number 33.
34. And at the top it says 3.2, 33, but it's question 34.
Okay, yeah.
I think the
So
last.
those,
step of
like,
it-
if you're looking in the book, that's the like question number in the book that it would
Yeah.
correspond to. So, all right. No, I don't think that's the one that you're talking about, though, is it? Or is it?
They didn't have it.
Is this what you're talking about?
Yes, sorry. It's like on the view the example, because if I'm not sure, I will walk through on view the example on how to step by step how to do it. And the last part, it just shows how the X, it shows a chart, like an
Okay.
X and a HY or HX, X and HX on the view the example on the last part of it,
Okay.
because the first few steps I understood, it was just like one step of it, you had to make a chart.
All right.
And
Let
fill
me
the
just go
chart
to this from my side so I can just jump to seeing the whole question.
And the numbers
Um,
there, like it was 0, 1, 2, 3, and they weren't in the question and they weren't, given. So that's why I was asking, is it just numbers
Yeah.
automatically I'm supposed to know?
And I would say most likely it's just, but I want to actually look at it and not just answer based on what I think it probably is. Let me just,
That's what I assumed it was too. It was just
Uh,
thinking it was,
question
a
30.
given, but I
oh, no,
wanted
it's
to double check.
34. All right. Okay, so I'm not seeing, are they just, okay, so they're just saying like, so you're choosing the graph
Mm-hmm.
from multiple choice, but they wanted you to
Yep,
just
keep going.
find some points.
There's
Um,
several steps to it. And then like
so-
if you go through the examples, it'll show how you make a chart, the X and
Yeah.
HX.
So it said find additional points in graph, but what you actually, like you're choosing
Yeah, it's
the
that
graph.
part of it. Mm-hmm.
So what I would look at is, so you had kind of these 2 points of 5. So an X value of 5 went with H value of 9. And then you had 11 going with 7 or whatever numbers you had. So you
Mhm.
had kind of those 2 pairs that gave you points on the graph. So as you're looking at that and you have this multiple choice, does that 5, like it needs a 5 and a 9. So like I can pretty much tell, because this is 5, 10, 15,
I
like
pretty much understood that
none
part.
of these. So you really didn't need to even find the additional points necessarily.
But if
So
I
sometimes the show me
hadn't,
example will go through a process that isn't necessarily how you have to do it. There are shortcuts. So I would say the shortcut is it's multiple choice.
Right,
Look at the
right.
examples and find the one that fits what you already have. But let's say you had 2 of these graphs that had, one, had the points that you needed, and then you had to figure out. So maybe I know that I need these 2 points, but maybe I have one graph that looks like this, and maybe I have another graph that, looks like this or something, but they have the 2 points. And so I can't tell just based on those 2 points. Then I would need to pick some other value. Maybe see like, what if I plug in this number? Does it come out? So that's where you would potentially need to pick other
Okay,
points.
so that's where the number comes in. You just say what if, so you just pick a number in between those 2 points.
Yeah, so some other number where you can
Okay.
tell like, okay, this number, the 2 graphs that I'm looking at are definitely different. So this number will allow me to figure out which graph is correct. But yeah, that's kind of a weird when it's multiple choice like that. If you were just needing to draw the graph and you just had those 2 points, then you would need a little bit more. But that's where then as you get into 3.3, or at 3, 4, then you know because it has the x squared, it's going to be a parabola shape.
Right.
Otherwise, you just have to do a bunch of points to kind of see the pattern. If you don't know that x squared means parabola shape, then if you're just looking, maybe you're just seeing this part of the graph and you think, well, okay, maybe it's kind of curving, but maybe it's just a straight line. If you don't happen to get this piece of the graph, then you don't really know what's going on. So
Okay. All right. So yeah, I was just wondering where they got their set of numbers from, and you're picking a set of numbers in between your 2 points to see if it works out, to see if I can make the statement true.
something like that. Yeah,
Okay.
that seems like a reasonable way to
Okay.
express that. Yeah.
Yeah, I got it. Thank you so much.
All right. Where's that? All right, we still have a few minutes, so let's see if I can hit the things that I know. Just kind of a heads up to recommend that you spend, plan to spend a little bit of time on. So for polynomials, the main thing that I see cause trouble is multiplicity, just because that's a word you may not be familiar with. And so you have to learn what it means to know what to do with it. It's really not complicated. If you're looking at factors, so let's say I have something like this. Multiplicity is just what's the power on each of those factors. So if I look, or you can say how many times did this 3x, that would be a 1 because there's nothing, it's just there once. This one, 2, this one is 1. So if it's squared, if it has a power on it, that's the multiplicity. If it doesn't have a power on it, it's 1. Then you have to know what to do with it. That's going to determine the shape, or whether it crosses the x-axis or just touches the x-axis. So that's the thing to do, that multiplicity tells you. But to know what the multiplicity is, again, it'll be, if you look in the videos and in the book and stuff, it's all there. But if you just try and guess based on the word, you're going to have a hard time. And then the other thing is it'll ask you something like the end behavior, where it won't necessarily clearly say what it's asking, but if it's asking the end behavior of the polynomial, what function does it act like? It's asking for the leading term is what you're going to be looking for. So if I want the leading term of this polynomial, I don't have to fully multiply it out into standard form. I just need to take kind of all of the highest power of x from each thing. So let me rewrite this out. So I had the 3x here times x minus 1 squared times x plus 4. So I'm going to take all of the x pieces, any coefficients on the x's. If the factor is squared, that gets included. To look at, if I did multiply this all out, what's the term that would get all of the possible x's multiplied together? So I'd have the 3x times the x that's getting squared times the other x, and that comes out, in this case, 3x to the 4th. And then it's helpful to know you kind of have 4 possibilities for the end behavior. Whatever it might do in between, it might have all sorts of ups and downs, but end behavior, up on both sides, down on both sides, up, right, down, left, or up, left, down, right. These ones are going to be if it's an even degree. These are if it's an odd degree on that leading term. And then the ones that go up to the right, are a positive coefficient. The ones that go down to the right would be negative coefficient. So it's really even, odd, positive, negative, like that. They'll describe it in the math lab in terms of x approaching infinity or negative infinity, and f of x approaching infinity or negative infinity. So approaching infinity is going to the right or going up. Negative infinity is to the left or down. So some terminology to learn with that, but that's the basic concepts. For the rational functions, I'm just gonna say this much. You're gonna have these giant problems with like 17 parts to them, so be mentally prepared for that. They are a pain. That's just the way MathHub decided to set it up. So don't just look at the number of questions, know that they're going to have tons of parts to them, but the parts that are most important, I think, for you to be able to get, even though they're all kind of equally counted, make sure that you learn how to find the asymptotes, make sure you're finding the intercepts correctly, and the asymptotes is the big one. There are other details that, you know, you can put your time into, but make sure that you're solid on the asymptotes and intercepts. But that's my time. So as you get to that, you want help, you want to see examples done of those polynomials, of those rational functions. Plan to obviously you have the section videos, all of the stuff in your learning activities page, so definitely use those still. But you'll also have the live lecture on Friday, covering polynomial stuff mostly, and on Saturday focusing on the rational functions. So let me bring up the this. So you have this link. I'm gonna see if I can copy this link and put it into, I'm just gonna type it in here. But yeah, please do go here, and just so we know who was here and any feedback you have about the session. Put that link in the chat also, so you can go to that. And you can do that. And if there's any other questions anybody has, as we wrap up, but I'll wait just a little bit, give you time to get that link. I'll go ahead and stop the recording at this point, but I'll keep the room open for a few minutes.